This is Unit 10, Lesson 9, Logarithmic Word Problems. And in these word problems, we're going to use some common formulas for the different categories of word problems that they have. And some of the common formulas are, if the problem mentions that it's a compound interest problem and they tell you that the interest is compounded and they give you every year or every month, every day, different things like that, then that would be a compound interest problem where they are telling you how many times or n number of times that it is compounded. Another type of compound interest problem would be a continuously compounded interest. If it's continuously compounded, it will state in the problem that it's continuously compounded, and you would use this formula. Now notice, in these formulas, like this one doesn't have an exponential, so it's a little bit more straightforward than this one. But most of your formulas, in order to solve them, you will need logs or natural logs to solve them. So that's why we put these type of problems in this chapter. So here, a equals pe to the rt. Your e is your exponential function. And then we have two other types that we haven't discussed yet, appreciation and depreciation. So if something is increasing in value over time, it's appreciation. So like you might think of a car, if it's an antique, the value of that car will appreciate over time after so many years. I think it's 30 years to become an antique. Same thing with furniture. If you have antique furniture, that furniture can appreciate over time. But if you're talking about a new car, usually a new car would depreciate in value. In other words, the longer you have that car until it becomes a classic, it will depreciate or decrease in its value. And pretty much anything you buy that will wear out, like a computer, a coffee maker, anything like that, a toaster, anything that you buy can depreciate in value because eventually it's going to break and you'll have to buy a new one. So it's going to become worthless over time. Things like paintings, they would appreciate over time if it's like from a famous artist. Different things like that. So appreciation, depreciation, depending on what you're talking about, you would use one of these different formulas. And with each of these formulas, I have given you what each of the variables represents, and that information you can get when you read the individual problems. So the best way to learn this is to just do some examples. So that's what we're going to do. In the first one, it says John is saving money to go on a trip to Europe after his college graduation. He will finish college 5 years from now. If the 5-year certificate of deposit he buys pays 7.25% interest compounded continuously, how much should he invest now in order to have $3,000 for the trip? So this tells you that it is compounded continuously. So that reading right there tells us which formula we should use. So we're going to use the compounded continuously equation here. A equals PE to the RT. Now, A is the amount or our future value, what it will be worth after that 5 years. P is your principal amount, the initial value. How much did he invest at the beginning of the problem? R is your interest rate, and remember, whenever you put a rate in, it will be a percentage in your problem. You have to write it into the problem as a decimal. And T is the amount of time. So we know A equals PE to the RT is our formula, and we're just going to plug in. So A is the amount or the future value, P is the principal amount. It says John is saving money to go on a trip to Europe. He will finish college 5 years from now, so we want to know how much is in there after 5 years, so that would be my T value, 5 years. If the 5-year certificate of deposit he buys pays 7.25%, that is my R value, my rate of interest. It's compounded continuously, which helped us understand that's the formula we're using. It says how much should he invest now in order to have $3,000 for the trip. So they're telling us that the future value they want us to have is $3,000. So that's what our A value will be, $3,000. That's how much he wants to have available when he graduates from college. They want to know how much we're supposed to invest. So what we're trying to find here is the P value. We don't know what that is. E is our exponential. Our rate is 7.25% as a decimal, which would be 0.075. 0.725, and make sure you include all of the decimals that they'd include, or all of the point values that they included. So when you move this to 2 decimal places to the left, it would be 0.0725. Don't leave off that 25. Very important there. And then the t is the amount of time, and we know this problem is taking place over 5 years. So to solve this, we could figure out in Desmos what this value right here is. So we need to figure out what e to the 0.0725 times 5 would be. So next I'm going to put that into Desmos. So here I am in Desmos. I put in e to the, and that is 0.0725, and then still as an exponent a 5 up there. And that gives me 1.4369. So I will round that to 1.437. So I'm going to go back. So I have 3,000 equals p times 1.467 when I round to 3 decimal places. And then if I do 3,000 divided by that 1.467, I will get my principal amount. So I'm going to go back into Desmos, and this time I'm going to put in 3,000 divided by 1.437. And that gives me $2,087.68 if I round. So my answer is $2,087.68. That's how much we need to initially invest in order to have the $3,000 after a 5-year period. For this one, it says the population of Antlers, Oklahoma is about 2,500. Suppose it is growing at an exponential rate of 3%. Determine how long it will take the town's population to double. Now, this one looks very similar to the ones we did in the last section to me. So for this one, I'm going to use the y equals ne to the kt problem. Now, they gave us a percentage rate here. This percentage rate is going to represent our k value, but we have to put it in as a decimal. Okay, so if I put that in, I've got y equals ne to the kt. To plug into this, it's telling us that the population of Antlers, Oklahoma is 2,500. And it's growing exponentially at a rate of 3%. Determine how long it will take for the population to double. Okay, well, our initial value, our n value is 2,500. That's what we start with. How much would the population be when it doubles? Hopefully you're saying 5,000. So that would be our y value, our final amount. So if I plug into this, our n is 2,500. Our k is our percentage as a decimal. That's 0.03. We don't know how much time this is taking, but our final amount will be double the size of the original, which is 5,000. If I divide 5,000 by 2,500, I get 2. I can put a natural log in front and divide that natural log of 2 by the 0.03 to get my t value. I will go back into Desmos. So I would have natural log of 2 divided by the 0.03. And that gives me 23.105 when I round it. And I think it's asking me how many years before my population doubles. So that would be approximately 23 years. In the next problem, it says some years ago, Hannah invested $10,000 at 12% compounded monthly, and the account now contains $30,000. How long ago did she start the account? Okay, so Hannah invested $10,000. She invested that $10,000 at 12%. It's compounded monthly. Now, a common mistake for this is people sometimes use the continuously compounded interest equation for this, y equals PE to the RT, but we know that if it's compounded monthly, they've given us a number of times it's compounded. So we're not going to use the continuously compounded equation for this. We're going to use the other compound equation for this. So this is the formula we're going to use. A equals P times 1 plus R over N to the NT power. So this is a compound interest problem where it's compounded monthly. Now, if it tells us that it's compounded monthly, that means our N, the number of times it's compounded, N is the number of times. So it's 12 times in a year. Our A is our final amount. P is the initial principal balance, that was invested. So it says some years ago, Hannah invested $10,000. That's her P value, the amount she invested. The interest rate, our R value, is 0.12 because we have to write it as a decimal. Compounded monthly tells us N is 12. And the account now contains $30,000. That's our A amount. How long ago did she start the account? So if we use the formula, A equals P times 1 plus R over N to the NT. A is 30,000 equals P, our initial amount, 10,000, times 1 plus R is 0.12 over N is 12. N again is 12. We don't know what T is. That's what we're trying to find. So if I solve this, I'm going to divide by the 10,000. 30,000 divided by 10,000 is 3. 1 plus 0.12 over 12. I can do that in Desmos. 1 plus 0.12 over 12 is 1.01. So this is 1.01 to the 12t power. So let's think about this. How can we solve this? Well, there are a couple different things we could do. We could put a natural log in front of both sides, or we could put a log in front of both sides. It doesn't matter which one you do, they would give you the same answer. So I'm going to put a natural log in front. Natural log of 3 equals natural log of 1.01 to the 12t. Now, when I do this, keep in mind your properties. I can take this 12t and move it to the front using my properties. So that would be natural log of 3 equals 12t times natural log of 1.01. And then I'm going to divide by everything but the variable. So I'm going to divide by everything that's not t on both sides. So this would be 12 natural log 1.01. I'm dividing by that on that side. And on this side, I'm going to do the same thing. 12 natural log 1.01. I'm going to do that division. So when I do that, over here, the 12 natural log of 1.01 cancels, and I'm left with t. For this one, I'm going to plug that into Desmos. So if I go into Desmos, in parentheses, I'm going to put the natural log of 3, and that's over 12 times the natural log of 1.01. And that should give us what we need there, 9.2008. So our time is approximately 9.2 years. So she started the account 9.2 years ago. For the next, a $12,000 machine depreciated exponentially, losing each year 8% of the value it had at the beginning of the year. What is the value of the machine 6.25 years after its purchase? Well, it tells you a depreciation problem. So our formula for depreciation is V equals C times 1 minus R to the T power, where C is the original cost. So they switch the values around or the variables around a little bit here, but it's okay. We can do that as long as we have this key there. A $12,000 machine. So if it's a $12,000 machine, that's our initial investment, our initial cost, original cost. That would be our C value. It depreciates exponentially, losing each year 8% of its value. R then is 8% or a 0.08 as a decimal. What is the value of the machine 6.25 years after its purchase? So T is time. The 6.25 would be our T value. B, the value, equals C times 1 minus R to the T. If I plug in, my initial cost was $12,000. I have a 1 minus, our rate is 0.08, and our time is 6.25. So if I plug all of that into my calculator or into Desmos at the same time, I should be able to get the answer pretty easily. So if I go into Desmos, so you can see I've put it into Desmos, and that gives me a 7,126.15 if I round. So that gives me a new value of 7,126.15. And anytime they're asking you about an amount of money, do that in dollars and cents. So you would always round to 2 decimal places. So our new value after 6.25 years, the machine is now worth $7,126.15. In the last problem, it says an oil painting from the early 20th century, originally purchased for $8,500, has been increasing in value by 7.5% for the 24 years since the purchase. how much is it currently worth? It doesn't actually say this in the problem, but it's telling you that it's increasing in value. And when you talk about something increasing in value, that would be an appreciation problem. So I want you to go ahead, pause the video, see if you can get this one on your own, and I'll give you the answer in a few minutes. So here I've plugged in. P is 8,500, R is 0.075 if we convert that to a decimal, and the time span was over 24 years. So if I plug into the formula, I have A equals 8,500 times 1 plus 0.075 to the 24th. And then I will go to Desmos. And you can see in Desmos, it's giving me a $48,219.43. So my answer here is a $48,219.43 if I round to the nearest dollar and cent. So I would say over a 24-year period, that is a pretty good investment. $8,500 turned into $48,000.